Lecture 9, Caching. In the words of a friend of mine, caching is very hit and miss. Or alternatively, if you prefer, cache rules everything around me. I don't think that's what they meant when they recorded that song, but they weren't wrong. Okay, so caching is very important in computing, and it's really not just for memory. Caching is examined in that context here, but it's applicable anytime we have a large resource that is divided in pieces, some of which are used more often than others, recognizing that more often than others may be like in a short period of time. Right, it might be that on average every company gets accessed, every month, but it might be when a company has been accessed, it implies that it'll be updated again shortly thereafter. We'll talk about it, as I say, in the context of memory, but we could use it for basically any application that meets the right criteria. Now, the thing is that caching provides benefit in some circumstances, but it's not useful in others, hence why it's hit and miss. So it's not a magic solution to everything. If we have basically no way of knowing what people are going to want to look at, then it's probably not as useful as it is if we know that people want to look at the same thing repeatedly, or given that they've looked at thing A, we know they're going to look at thing B. Those kinds of things are helpful. But why do we have caching? Well, the main goal of caching is to speed up operations. And we'll talk about like CPU cache as an example, but again, it applies for other scenarios as well. But caching is hopefully getting information faster than it would be if we had to get it from somewhere else. As far as the CPU is concerned, getting something from the cache is faster. It takes less time to get data from cache to the CPU than it takes to get from main memory to the CPU, primarily because cache is smaller and more expensive kind of memory, but also because, well, it's closer, right? If we have to go to cache, well, cache is located on the same die as the CPU, whereas if we're going to main memory, it requires going out over the system bus to communicate with main memory that way. As we know, CPUs are much faster than memory, and it's best if we don't keep them waiting. Caches don't have to operate on pages. As I talked about previously, you could have caching around companies or around data elements or accounts or anything you can think of. But a cache typically operates on blocks of a given size. And an entry in a cache is often called a line, so we talk about cache lines and cache storage and all that. We're going to assume, just to make the balance of the discussion a little bit easier, that a cache line maps very nicely to a page, and a page is whatever your operating system is implementing for its convenience. As we've discussed, cache pages are probably dominated by disk reads, and we've used the 4 kilobytes example. Let's imagine it's that, right? So a cache line in this case corresponds to a page. So if we have X kilobytes of cache, we divide that by 4K to find out how many possible entries we can keep in the cache at once. And so, as discussed, the CPU generates a memory address for read and write operation, and the address will be mapped to a page, and best case scenario, the page is in the cache. If that happens, we call it a cache hit. That's faster, of course, than getting it to the CPU from main memory. And if the page is not found in the cache, we consider it a cache miss. And in the case of a miss, we have to load the page from memory, which is a comparatively slow operation. A page miss is also called a page fault. We should also take a note that typically when we are retrieving the data from main memory, we're going to put it in cache on its way to the CPU in case we need it again in the future, which maybe we would. And yeah, the percentage of time that a page is found in the cache is called the hit ratio. And the hit ratio is exactly what it sounds like. It's just a way of saying the percentage of pages found in the cache. And if we have a good estimate of this, and it's not overly difficult to obtain, we can in fact just do some math for a given execution of a program to try to figure out what the hit ratio is. And we know some measurements of how long it takes to load data from the cache versus how long it takes to load from memory. We can calculate the effective access time. And this is an average time. It just says anytime we want to read or write from memory, how long, on average, do we think it's going to take? And the effective access time is computed as the formula shown on the screen. It is H, the hit ratio, times T sub C, that's the time required to load a page from cache, plus 1 minus H, so the percentage of the time that we miss, times T sub M, the time to load a page from memory. And that seems intuitive, I guess, or at least sufficiently straightforward that I don't have to belabor the point, that if we find something in the cache 80% of the time, it'll be 0.8 times the time that's found in the cache, plus 0.2 times the time to retrieve something from memory, and that would be good. Now, of course, any individual read or write will fall into one or the other of those cases. Either it's in the cache or it's not. The actual access time for a read or write will be different from the average. In fact, this is one of the scenarios in which the access time will most likely never be the average, because if it's in the cache, it's less than the average, and if it's not in the cache, it's above the average. But if you compute, over the total runtime of your program, how long it's going to take, the average is fine. Okay, so as you will imagine, we want the hit ratio to be as high as possible, right? That makes the effective access time as small as possible, and that means your program goes faster. Cool. Now, caches have limited size because faster caches are potentially expensive, right? With infinite money, maybe we could put everything in registers. There are some physical component limitations for how you place it all on the chip that would kind of make that impractical after a certain point. But I think it is fair to say that if we had more money, we could put more registers, right? Not always, but at least based on current space. However, it turns out there is a limit to what people are willing to pay for CPUs. If Intel and AMD don't always act like they know this fact, but it does turn out to be the case. And caches for memory are very often multi-level. Just for an example, like a 64-bit Intel CPU tends to have level 1, level 2, and level 3 caches, usually abbreviated L1, L2, L3, and sometimes even L4. L1 is the smallest and the fastest. L3 is the largest and the slowest, and level 2 cache is somewhere in between, as you would expect. And obviously you would update the expected access time formula to account for the fact that there are different levels, given that we are now talking about, okay, what's the hit ratio for level 1 times its speed versus what's the hit ratio for level 2 times its speed, and then level 3, and then finally main memory, right? If we issue an address and we find it in level 1 cache, excellent. If not, we check level 2. If it's there, good, we're done. If it's not in level 2, we check level 3. Again, if it's there, good. If not, we have to go to main memory. Either way, when we retrieve the page, wherever we retrieve it from, if it's not in level 1 cache, we're going to copy it in. If it's not in level 2 and we're retrieving it from level 3 or main memory, it's on the way. It's always copied into the in-between levels on the way in. Well, that means necessarily that there might have to be space made for that thing, right? Caches have limited size. We talked much earlier on in a review of computer architecture about the various sizes for level 1 cache. And, total cache might be a few megabytes, but level 1 cache could be fairly small, measured in kilobytes. So we're going to have to make some space for the thing that we would like to bring in. We're going to have to manage that space quite carefully. So how should we do that? Well, whenever a page fault occurs, right, we're going to have to make a decision about what should be evicted, kicked out of cache to make space for a new page. This isn't always easy, but we got to do something, right? We're also going to assume that the cache is full, which is likely to be true except at the very beginning of time when the system starts up. Like I say, because we're talking about something that's measured in kilobytes, I think we can be reasonably certain that it's likely to be full at all times. And we could select a random page, and again, we would like to do this intelligently. You might consider random page in an evaluation just as a baseline, but I think we can probably do a little bit better than that. Now, to make an intelligent decision, we have to know about how data is accessed in the system. Or at least it would be helpful if we knew that. And I've already mentioned a couple of things that I think are likely to be interesting or likely to be helpful. One is it would be good to know if something that has been accessed recently would be accessed again. Another thing is it would be interesting if we know any predictions. Like if this is looked at, then does it indicate that we're likely to look at the next thing in the sequence? Okay. So there are three things that are observed, if you will, empirically in how caches work, at least around memory. Number one is this 90-10 rule, which is about 10% of the source code will be executed 90% of the time. This is a variant on the Pareto principle, which is referred to as the 80-20 rule sometimes, which is 80% of the thing is represented by the key 20%. The Pareto principle kind of thing is good in some situations, but it's not perfect for everything. In the notes, I comment that if you study very effectively 20% of the course material, it's unlikely to earn you 80% of the marks. But yeah, like I say, it's not necessarily useful in every situation, but it is useful in many situations. But the things that are interesting to us are, how often is particular code executed? And you'll probably find, when it comes down to it, that the majority of time spent executing code is executing what you might call sort of the happy path, right? The stuff that happens normally. There's no error, there's no issue, everything happens according to plan. But you have a lot of code in whatever program you've written that handles unusual situations, right? Like what if this customer wants to do X, but the third party is down? Right. Well, they're down for maintenance, 1 hour a month, according to their service level agreement that you've signed with them. So the code that says, oh, sorry, please try later, our partner is down. Well, that executes 1 hour of every month. That's not a lot. So, majority of time is spent doing the normal things. And similarly, you have probably a lot of error handling code and other things that don't run very often. That might seem sensible, that there's some sort of 90-10 rule or 80-20 rule or however you want to think about it. However, the more interesting things to us are these principles of temporal locality and spatial locality. And temporal locality says a memory location that has been recently accessed is likely to be accessed again in the near future. And spatial locality says a memory location that is near a memory location that has recently been accessed is likely to be accessed in the future. So a quick example of code that would actually show both temporal and spatial locality is summing up all the values in an array. The sum variable is something that's accessed repeatedly. Every iteration of the loop, you are updating the sum variable with the new total. Because it was recently accessed, it gives you a hint that we're probably going to update it again soon. Right? That's how the summation works. We're just going to keep updating the sum every time we do another iteration of the loop. And spatial locality is shown because when we iterate over this array, we've accessed the array at index I, and having done so suggests it's likely that the array at index I plus 1 is likely to be accessed soon. Assuming that the loop is iterating over the array one element at a time. We're not skipping anything. We're not going to break out of the loop. So all of those are hints as to, hey, this is something that's likely to happen in the immediate future. It's not a guarantee, right? There are certainly possibilities that we're going to break out of the loop. We're finished what we're doing. The request has been canceled by the user, whatever it is. So our calculation, our assessment here that says the array at index I plus 1 is likely to be accessed soon is by no means a promise. It's by no means a guarantee, but the pattern is important. Now, if a page has been altered in cache, then the change will need to be written out to main memory at some point. And we have choices. Number one, we could do it immediately when the page is changed, or it can be done when a page is evicted from the cache. The second option potentially means fewer main memory accesses, particularly if a page is written to multiple times before it's sent to main memory. If the memory is shared, used by another process or even potentially another thread, or shared with an I/O device, then the delay in updating main memory might not be okay, in which case we have to actually forcibly write it out. So if we want to bring in something new and we have to make space, it's probably better, if we can arrange for this, to just overwrite something that hasn't been changed, a page that's only been read but not written, so that we don't have to do the work of writing it out, all other things being equal, right? We're not always going to get that behavior. Overwriting with the new one is nice, but if all other factors are equal, we should replace a page that has not been modified so that we can minimize the amount of work that we need to do. Okay, so the first algorithm that we're going to talk about for cache eviction, page replacement, if you will, is the optimal algorithm. And the optimal algorithm is actually very simple to describe. It says replace the page that will be used most distantly in the future. That is to say, for each page, make a determination about how many instructions in the future that page will be accessed. The selected page is the one with the highest value. Well, that sounds pretty straightforward, right? Well, I'll give you a hint. If this was the only algorithm that we were going to talk about, why would I start with why would I call it the optimal algorithm? If we're going to talk about several ones, why would I start with the perfect one? Because what's the point of talking about other ones that suck in comparison to this one? No. That's obviously... there is a glaring flaw in this algorithm. It is impossible to implement. It requires clairvoyance, seeing into the future. I am acutely aware that Saruman here is using a Palantir and they don't actually see into the future. There's seeing stones kind of thing, but and it's easy to get lost in the Wikipedia article about Palantir and how Saruman uses them and their appearances in Lord of the Rings and how they work and all the Lord of the Rings related subjects. I know they're not actually foreseeing into the future, and in fact what they show you might not even be true depending on who is presenting it and if they want to deceive you. But listen, I wanted, like looking into a crystal ball fortune telling kind of thing, and I came across this idea and I thought, you know what, I just would much rather have Saruman and a Palantir in the presentation than just a cat saying, yeah, I'm going to look in the crystal ball with impact font at the top and bottom. So okay, Lord of the Rings digression aside, why do we talk about the optimal algorithm? Well, you can think of it as a benchmark, right? It's a hypothetical that we want to compare other algorithms against. Now, you can look backwards at an actual execution of the program, and you can say, okay, if we had made the optimal choices, what would have happened? And that will give you an answer to the optimal algorithm's performance. And then you can compare that against the actual performance of your program, and that will help you to evaluate whether the replacement algorithm that you're using is good or not. Right? If the actual algorithm that we used is, say, 1% less efficient than the hypothetical optimal, the one that required us to look backwards and, Monday morning quarterback, if you prefer a sports analogy, what happened, then we know that we won't try to waste any time improving this, because if we did, the maximum performance increase would be 1%. If we do find, however, we're doing much worse than the optimal algorithm, it suggests, well, maybe doing something a little bit different would yield more opportunity for speed up or for benefit, right? So let's talk about some algorithms that are actually possible to implement. So first one is called not recently used. And operating systems can collect page usage statistics and use status bits associated with each page, which we will call R and M. And R is referenced, M is modified. And the R bit is set whenever a page is referenced, whether that is a read or a write. And the M bit is set when the page is written to, that is, modified in some way. Once a bit is set, it remains so until the operating system changes that value. So initially, R and M are 0. That is, they're not set. And periodically, the R bit will be cleared to identify pages that are not recently referenced. That might happen on a clock interrupt, for example. We say, okay, if it hasn't been referenced in the last 1 second, then we'll say it hasn't been recently referenced. Remember that from the computer's point of view, 1 second is a very long time. As Commander Data says in First Contact, for an Android, it's an eternity. Now, let's say that we have a page to replace. So we'll examine all of the pages and we'll sort them into 4 buckets based on the R and M bits. So there's not referenced, not modified. So it hasn't been used recently and it hasn't been changed. There's not referenced but modified. So it hasn't been used recently but it has been changed. Number 3, referenced and not modified. So it's been used recently but has not been changed. And then there's referenced and modified. So it has been used recently and it has been changed. And we prefer to remove a page from the lowest numbered class when possible. All right, the not referenced, not modified is best case scenario. We don't need it, or we don't predict that we'll need it in the immediate future, and we don't have to write it out. It's up to date in main memory, so we'll just overwrite it. Not referenced and modified requires us to write out the page to main memory, but at least we're working on something that hasn't been used recently. If we can find nothing in either of those categories, then we'll go to ones that have been used recently, and we'll, again, prefer one that hasn't been modified since we can skip writing it out to main memory. Does this work? Well, yeah, the not recently used algorithm is fairly easy to understand, and it may provide adequate performance. We'll take it. But maybe we can do better. So first in, first out is somewhat easy to understand and implement, and it does provide some sort of temporal locality. If there are n frames, we just have a counter that points to the frame to be replaced, thinking of it as like a linked list or a circular buffer or something like that. And whenever a page needs to be replaced, we replace the page at the current index, increment the counter, just wrap around to 0, and we get to the end. This one's a little bit harder to evaluate, right? Like, does this actually do what we want? When we load a page, we keep it around for quite some time. If there are, let's say, just to make it nice round numbers, 10 spaces in our cache, when we load a page in there, it's going to stay in there until 10 replacements have taken place. But does this work? Sometimes yes and sometimes no, right? If the page that we're referencing is going to not be referenced again, or at least not be referenced for a very long time, it's a good choice to get rid of, right? If we load data, we process that data, and then we never need that data again for the operation that we're doing, throwing it away when it gets old is fine, and that kind of makes sense. But on the other hand, frequently the same page is referenced repeatedly, and this algorithm does not take that into account. If a page is referenced frequently, we want to keep it in memory. As Obi-Wan says, it's a system we cannot afford to lose. We don't want to evict it just because it's been in the cache the longest. And in the case of like summing up a large array into, let's call it a summary structure, it doesn't just have to be an integer that you're imagining, but we're summing up some statistics about it. We'll see that first in, first out works pretty well for the array itself, because once we're finished with a section of the array, we don't need it again in the immediate future. But it doesn't work very well for the page where the summary information is being stored, because we're using it a lot. We use it on every iteration of the loop, and yet when it gets to be the oldest in our cache, it gets thrown out. So we don't want that, right? It's annoying that it has to get kicked out and loaded into cache again every single time, because we would prefer to keep it if we would like. So it's probably not the best choice. Is it possible to use it? Maybe. But let's just say it's not our first choice. So, as Pippin says, what about second breakfast? And what we're going to talk about is a second chance algorithm. And it's going to improve on the first in, first out, but we will give a page another chance. If it gets selected, it can stave off its dark fate for just a little bit longer. I don't think he knows about second breakfast or 11 Cs. Okay, and this brings back the R bit, the referenced bit. And it gives pages a second chance based on this setting. So if a page has been referenced recently, that bit is set. If it hasn't been referenced recently, really since the last clearing of all those bits, then, well, it's not recently referenced. And what we're going to do instead of just kicking out the oldest page is we'll look at the oldest one and we'll see, has the R bit been set? And if the answer is yes, then we'll clear it and we'll go on to the next one. If the answer is no, great, this one is selected and we'll kick it out. This goes to the next oldest page and repeats the procedure, and we'll keep doing this until eventually we found a page to remove. Because the algorithm clears the R bit as we move along, even if all pages have recently been referenced, eventually a page will be selected and evicted, right? If they're all referenced, we will eventually wrap around back to the beginning, and when we get back to the beginning, we will find, all right, here's a page that has the R bit cleared because we cleared it last time we looked at that specific page. It's fine, right? The algorithm will eventually terminate. And the index is updated whenever this happens, so a page that got the second chance is not, quotation marks, the oldest anymore. And in some textbooks this is called the clock replacement algorithm because we can think of cache as a circular buffer. The current oldest page is depicted as being pointed to by the hands of the clock, right? And so like one of the hands is pointing to what is the current oldest page, and then as we iterate around, we're checking, can we kick out this one? No. Can we kick out the next one? No. And so on and so on and so on. So that's an okay algorithm. We'll take it. It does prevent the problem of a page eventually becoming the oldest and getting kicked out, only to get brought back into cache again immediately. What we're going to talk about is least recently used, and this is considered probably the best algorithm, at least as far as I know. So we should probably focus on this one, but we'll talk about other options as well. So the least recently used algorithm says the page should be replaced is the one that has been accessed most distantly in the past. You might consider, if you wanted to implement this, timestamps and then searching the list for when the timestamp was implemented, but it really doesn't have to be that complicated. Because there's only a couple of things, we don't have to do that. When a page in the cache is accessed, we just move it to the back of the list, and we evict the page at the front of the list. And if that's the case, if we have a cyclic doubly linked list, then it's very easy. It takes constant time to move things and takes constant time to remove things as well. So that's pretty good, right? We always remove the things at the head of the list if we have to do something, and when something is referenced, we just move it to the back. So that's nice. And then there is the not frequently used approach. And it's similar to least recently used, but it involves counting number of occurrences. How many times was the particular page referenced? And each page gets an associated software counter, starts at 0, and whenever the R bit would have been updated from 0 to 1, i.e. it has been recently referenced, we'll just add 1 to the counter, and when a page is to be replaced, we evict the page with the lowest counter value. Does this seem like it has a problem? Did we forget something important here? Yeah, like an elephant, it never forgets, right? NFU doesn't stand for never forgets usage, but I could see why you might think so. A page that was accessed very frequently at the start of the program can accumulate a high counter value very on, and therefore might not be evicted, even if it's not needed again, right? It's the future now. We don't need those things from the past. So what we actually need is a way for the count to decline over time. And the solution is called aging. And aging says counters are shifted to the right by 1 bit before the 1 is added. Instead of adding, we just set the leftmost bit to 1. So now we have a bit array of byte size, and a page that has not been referenced in a while has its value decrease over time. Now, we're still going to do a comparison on the value of the page, right? We're just going to evict the page that has the lowest value. We're still doing a comparison. Our mathematical tools, like in the CPU, work just fine for this, even though it's implemented as a bit vector. Just ages are a little bit more difficult to interpret by looking at them as a number. As a human, when you see the value of this is 32, it doesn't mean it was referenced 32 times. It just means the 1 is located in that position in the bit vector. We do lose a little bit of precision as compared to the LRU approach. If pages A and B both have usage patterns of 7 zeros followed by a 1, we know they were both last accessed 8 cycles ago, where cycle in this case refers to the information about like when we shift it and when we mark something as 0 or 1. And all history before that point is lost. Which page between A and B has been recently used is no longer clear. Now, it's okay, honestly. Nothing of tremendous value is lost if we don't have the most precise between A and B. If they're both equally, quotation marks, old, as far as we're concerned, that's good enough from our point of view to just pick one or the other, right? The algorithm doesn't have to be perfect, it just has to pick something. I'll also note that what we've talked about so far has always been sort of on demand. It's been reactive. Only when a page is needed and it's not found in the cache do we make the effort to actually load it into the cache. In principle, we could guess about what pages we think might be needed next. It might reduce the amount of time spent waiting for a page in the future. That's hard though, right? In some cases we can see we're iterating over an array. We could recognize this is a pattern, and based on that pattern we could predict, okay, we're probably going to need the next page that contains data from this array. But it's only a guess, and our guesses in this case could be wrong. Predicting which pages are likely to be used in the near future is a certain amount of clairvoyance. There do exist techniques to determine likely pages to be used frequently, which are sometimes called the working set. That's kind of complex. We're not going to talk about it in this course, but there are situations where you might want to try to predict things. Pre-paging is somewhat useful, say when we're starting a program or we're swapping it into memory. Technically, no pages need to be in the cache to start with. We can just suffer page faults as we demand page everything. But it could be interesting if you wanted to try to squeeze out a little more performance to guess about which pages would be needed and potentially speed up that program. But if you wanted to think about, here's how we would do it. The algorithms are sort of broken down to comments. This is quite high level and it skips over a lot of the nuance. But it's going to tell us something interesting about which ones we would like to use. Optimal algorithm, as I said, is impossible to implement, but it makes for benchmark. Not recently used is not very good performance. First in, first out is the kind of thing that Professor Harder would describe as highly suboptimal. The second chance algorithm is better than first in, first out, just adequate. Least recently used is the best performer, but it says difficult to implement. Why? Because it works best if there's hardware to support it. If not, then, well, the not frequently used with aging is the best approximation that we can get. Unless there's a specific reason to choose one of the other algorithms, LRU, least recently used, is the one that is most likely to be the algorithm that we select. Now, when a process switch occurs, we could make an effort to just dump the entire cache to make way for the next process to run, but that is most likely unnecessary work, right? If process P1 is suspended now, it's blocked on a semaphore, let's say, process P2 can run for a while, and then P1 runs again. And if P1 has some stuff in the cache still, well, that's great, right? We would like to keep those because we need them. If P2 did replace all the cache lines, that's sort of worst case scenario from the performance of P1's perspective. But if we went out of our way to replace everything from P1, we maybe just did some unnecessary work. Realistically, though, we will have multiple processes with pages in the cache at a given time. And if we are going to do a replacement algorithm, we might give some thoughts to the idea about whether we do a local or a global replacement. A local replacement says, well, we want to replace, say, the least recently used page that belongs to the current process. Or do we want to do the global replacement option, which is we replace the least recently used page in all the cache, which is global replacement? Either one of those things could actually work. It's a design decision which of those we think is going to be better. Different levels of cache can also have different strategies if you just want to have some additional complexity to keep you up at night. Level 1 cache, if it's 16 kilobytes and there's 4 kilobyte pages, there's 4 pages in level 1 cache, so it doesn't make any sense to have reservations. If level 2 cache is 256 kilobytes, that's 64 pages. That again might be a bit too small for local replacement to work for us. When caches are somewhat larger, though, things may be a bit more interesting. Like maybe we don't want to allow one process to monopolize all of the cache just because it happened to run and generate a lot of page faults. So a local algorithm gives each process some fixed number of pages in the cache. Global algorithms dynamically allocate cache space to different programs based on their needs. The number of pages will vary. This one's been running a lot, so it has a lot of pages, or this one had a lot of page faults, so it has a lot of pages in the cache. That will probably happen. According to some research on this, in one of the textbooks that's referenced, global algorithms tend to work a little bit better, especially when processes' memory needs change over time. If a local algorithm is used, we may be wasting some of the space in the cache for a process that really does not need it right now. But if we have a large cache and some dynamic allocation using a global algorithm, we might choose to modify that a little bit to prevent any process from having too many or too few pages in the cache. So we don't want to let one process monopolize it to the detriment of others. But why would we be worried about too few? Well, a process that has too few pages has a lot of page faults. And to manage the complexity of this, we might wish to sort of keep track of the number of page faults using a measure called the page fault frequency. So this is, in simplest terms, a guide for saying whether a given process has too few, too many, or about the right number of pages in the cache. If the page fault frequency is really high, more cache space is needed for that process, and that's an issue. If it's low, below some lower threshold, it suggests the process has too much cache space allocated, and it could stand to part with some to let other processes have those things. Now, to my knowledge, not very many caching systems implement these kinds of things where they try to limit whether or not one process can monopolize it. but it's still interesting to think about, and could be relevant for a use case that doesn't jump to my mind immediately while I think about this. This does rely on the assumption that more cache space does mean fewer page faults. This is true for, say, the least recently used algorithm, but not necessarily true for the first in, first out approach. So, as if you didn't need one more reason to choose against the first in, first out approach, there are studies that show that using the first in, first out algorithm, adding more cache space can actually make things worse. So yeah, the more you know. Okay, this has been kind of a good digression on the subject of caching and memory and why it's useful in that situation, but it's not useful, as we discussed at the beginning, for absolutely everything. But digression aside, because we talked about the translation look-aside buffer and all that, we should circle back now to what we were originally talking about before, which was memory in general, and we're going to wrap up with a two-part discussion of virtual memory.